So in the previous class we were discussing about the state diagram representation as well as the code tree. So where we came to know how we are going to find the convolutional codes using state diagram representation. That means instead of using the time domain as well as the transform domain approach, so we can also calculate the convolutional codes using the state diagram representation as well as the code tree. So we came to know how we are going to construct the state diagram. So in order to construct the state diagram, so first we need to represent a state table indicating how many number of states do we have. So how we are going to write the state table is, so by looking into the convolutional encoder diagram, so we are going to write first the state table, then the next step is we are going to write the state transition table. That means if the state moves from one state to the other state, so what is its input and what is its output, and if it remains in the present state and if it moves to the next state, how its output is going to affect. So that we indicated with respect to a state transition table. So once we construct the state transition table, so from the state transition table we are going to construct the state diagram. So this is how we are going to construct the state diagram by looking into the state transition table. So now by looking into the state diagram, so this is your state diagram. So from the state diagram, now we need to write or transfer this state diagram into a code tree. Okay. So now for this, let us consider that the message input, that is D. So it is 10111. Okay. And this is your, and these are the values with respect to n, k, comma, m, that is 212. Okay. So now if the transition, so if the transition starts from, or if the message input is 1, so whenever we are going to construct the code tree, so depending upon the message input D, so it is going to make a transition of the code tree upwards or it is going to make a transition downwards. So now how we are going to construct the code tree is by looking into this particular state diagram. So where we have first the state is S0. So this is your state S0. So this is your state S0 and you are going to input the message. Okay. So now you know that your state S0, it can make a transition either to 1 or to 1. So that means your S0 has two input states, that is input 0 as well as input 1. So if the input is 0, so then where it is going to reach? It is going to reach to S0 state. So if the input is 1, so then it is going to reach the S1 state. So similarly, so from S0, once again it is going to make a transition with S0. One is with respect to S0 and another one is with respect to S0. So now here, so with respect to your S1, we have two states once again. So one is with respect to S1 with input 0. So it is going to make a transition to S2. And if the input is 1, it is going to make a transition to S3. So it is 0, this is 1, this is also 0 as well as 1. So now again, so we have two states, S0 and S1. So S0 with input 0, S0 with input 1. So here S1 with input 0 and input 1 we have S2 and S3. So similarly with respect to S3, So what is S3? So for S3, if suppose if the input is 0, it is going for S2, and if it is 1, it is in S3. And in the case of your S2, we also have two states, so this is 0, 1, 0, 1. So with respect to S2, if the input is 0, so S2, if the input is 0, then it has 0 transition. If the input is 1, so then it is going to make a transition to S1. Okay. So now how many states we need to perform this kind of division of the states is until all the message inputs are traversed through your code tree. Okay. So now, so since we have the 5 bits here with respect to your D, so 5 bits means it is going to traverse through 5 successive stages. So that means what should be your length of the message bits here is, it is n into L plus m. So what is n here? It is 2. What is the length of your message code? It is 5 plus number of modulo adders, it is 2. So it is 2 into 7. So that means we should get 14 bits. But here what is the size of your message? It is only 5. It is 5 into 2. That means you are going to get only 10 bits. So what should we need to do with rest of the 4 bits is that, so we need to extend the tail of the tree. So that is called as the tail of the tree. So in order to extend your tail of the tree or the code tree, so we are going to perform this. Okay, n into m minus 1. So this is how you are going to extend the size of the tree. So n means it is 2. So it is 2 minus 1. So you are going to get 2. That means 2 stages you are going, that means 2 extra bits you need to append to the original message bits to find the tail of the tree or for the extension of the code tree. So now 2 means 2 extra bits means, so it is nothing but a pair of bits. So you have to append 4 extra bits. That means to say that, so your message input D will be equal to 10111. So this extra 2 bits we need to add it here. So that means extra 2 bits means it will be 7. Totally you will be having 7 bits. So whatever the extra bits we are going to consider here, which is called as the tail of the tree. So those bits are appended by zeros. Okay. So let us see here how this transition of the message input, that is D equals 10111, takes place with respect to this code tree. So this is how we are going to write the code tree here. So now for the input, that is depending upon the message input D. So let us check that what is the first message input we have for D is equal to 1. That means if your message input D is equal to 1, so that then the transition will occur downwards. Suppose if the message input is starting from 0, then the transition will occur upwards. So now we are interested only with respect to the downward direction of the movement of your message input. So that's why here, so we will consider this stage, but you need to show the extension of both the states, that is for S0 equals 0 as well as for S0 is equal to 1. So now further here we need to extend this stage. So this is S3. So this is how we are going to perform the extension of That means the state diagram is extended to the code tree. So this is how you need to divide depending upon the input 0 and 1. So now since your message input is starting from 1, so we are interested only with the downward part. So that's why, so we will just take only the transition with respect to 1. So this is your S0 with 0 and 1. So now we are considering from here. So this is S0, S0 and S1. So it is input 0 and 1. So further, so this is S0, 1 with input 0 and 1. So your S1, so with input 1 it moves to S2, and with input S1 it moves to S3. So further, this is S0, this is S1. So this is S0, and so from S1 it is S2 and S3, and this is S2. So from S2 it moves to S0 and S1. So from S3, so it moves to S2 and S3. So now considering the message input D is equal to 1, so we need to make a downward transition. So this is for the message input 1. So with S0 with input 1, so what is its output? So with input 1, so it is going to make a transition to, so from S0 with input 1, it is going to make a transition to S1. So this should be S1 with input 1. So and this should be S1 with input 0, it is S2, and this is S3, and S2 to S0 and S1. So this is with input 0 and input 1. So from S2, so from S0 with input 0, S2 with input 0 we have to S0, and with input 1 it is going for S1. So from S1 with input 1, so it is going to S3. So this is 0, 1. Okay. So now here, so what is the output? So with message input 1, so this is for input 1. So with S0 1, so what is the output we have? It is 1, 1. Okay. So we already have 1 here. So the output of this is 1, 1 with message input 1. So this is for the first bit. So next. So after that with 1, so where it is going to reach, it goes to the S1 state. So with S1 state with input 0, that means it has to make a transition upwards. So it moves to the state S2 here. So with S1 0, that means with S1 with input 0, what is the output? So the output is 1, 0. Okay. So this is for the input 0. Next. So again we have the input 1. So from this, so the input is 1. So from S2, if the input is 1, so where it is making a transition, it makes a transition to S1. What is its output? It is 0, 0. Okay. So next. So once it reaches here, so this is for when the input is 1, that is the third message input. Next message input is also 1. So for 1, it makes a transition to S3. So what is its corresponding output? S3 with input 1. So S3 with input 1, so it is 1 0. So this is 1 0. This is for the fourth message input. So now this is your S3. So I need only S3 here. So since I don't have space, I am going to erase it this one. So S3. So again it is divided into two states with input 0 and input 1. So S3 with input 0, it is S2, and again it is S3. Okay. So now S3 with input 1, where it is going to reach? It is going to reach S3. What is its corresponding output? It is 1 0. This is for the fifth message input. That means, so we have traversed through 5 different stages of your code tree. This is for the first message input 1. This is for 0 and 1, 1 and 1. So next further I told that we need to extend the tail of the tree. So how the tail of the tree is extended is by appending the next message inputs as 0. Okay. So now from S3 again we are going to extend it. So where again we are going to consider with input 0 and input 1. So it is S2 and this is S3. So with input 0, so what is its corresponding output? That is with respect to S3, if the input is 0, it is going to make a transition to S2 and the output of that is 0, 1. So further we are going to extend this. So with S2 with input 0 and 1. So with S2 with input 0, it makes a transition to S0. And with S2 input 1, it makes a transition to S1. So that means now we need to consider one more stage here with input 0. So what is the output? The output is 0, 1. So this is for the message input 0 and this is for the message input 0. Okay. So now this part, so this whole part is called as the tail of the tree. Okay. So this whole part is called as the tail of the tree. So because we have extended the code tree, so by appending 2 more message bits, so whatever the message bits we are going to append, so those are zeros. So this is with respect to the downward direction. So similarly, so the upper part, it is the extension with respect to the upper part. So this you have to extend further. So that is, you have to write S0, S1, similarly S0, S1. So all these stages need to be completed. So this is how we are going to find the code tree by looking into the state diagram. Okay. So whatever we have found out with respect to the code tree, that means the how your message input traverses. So corresponding to that, we found out what should be the output. That means what it is going to generate as the output depending upon the changes with respect to the message input D. So now, so this is the code word what we are going to get. So by looking into the code tree. So now we have to verify whether whatever the code we have got from the code tree is correct or not by verification with one of the transform domain or with respect to the time domain approach. So let us consider your transform domain approach and let us verify whether we are going to get the same code word. So from the encoder diagram, so we have G1 and G2 as 111 and 101 and we know that what is your message input D. So since we are finding with respect to the transform domain approach, we are converting that to the polynomials. So it is 1 plus x square and this is 1 plus x square x3 plus x4. So first we need to find C1 of x is equal to d of x into g1 of x. So d of x is x square x4 into g1 of x is 1 plus x square, so which is equal to 1 plus x square plus x3 plus x to the power of 4 plus x plus x3 x4 x5 plus x square 4 5 plus 6. So now x3 and x3, x4 and x4, x square and x square, then we have x5 and x5. So we are left with 1 plus x plus x to the power of 4 plus x to the power of 6. C is your C1 of x. Okay. So next we need to find what is your C2 of x. So C2 of x is d of x into g2 of x. So what is your d of x? So it is 1 plus x square. So multiplied by your d of x is what? Sorry, g2 of x is what? It is 1 plus x square. So this will be equal to 1 plus x square plus x square x to the power of 4 5 plus 6. So x to the power of 4 x square and x square. So we have 1 plus x to the power of 3 x power 5 plus x to the power of 6. So now we need to find what is the output C of x. So C of x is equal to C1 of x into x power n plus x into C of 2 into x to the power of n. So what is n here? So n is, so we know that it is 2, 1, 2. So this is n, k and m. So that means we have n is equal to 2. So if we apply n is equal to 2, then your C1 of x will be 1 plus x square 8 plus 12, and this will be equal to 1 plus 6 10 plus 12. So this will be 1 plus x square x8 plus 12 plus x into 1 plus x power 6 x power 10 plus x power 12. So this will be 1 plus x square x8 x12 plus x plus 7 plus 11 plus 13. So this will be 1 plus x square x7 8 11 12 and 13. So this will be, we have 1 1, we don't have, so we have x3 x2 x3 is not there, x4 x5 x6 x7 x8 x9 x10 11 12 13. Okay. So now if we pair with respect to 2 2, so if you compare now, so we have 1 1, okay, then 1 0 0 0, then we have 0 1 1 0 0 1 and 1 1. Okay, that means whatever we have found out from the code tree, so that has been verified by using any one of the time domain or the transform domain approach. So here we have used transform domain approach and we have verified the answer. So this is one more example with respect to representation of the state diagram and code tree. So this is the example. So draw the state diagram. So for the convolutional encoder block diagram shown in the figure with the message input D equals 10111, and we also need to verify using time domain approach. So now as you can see here, so we have only one flip flop. So your M is 1 and your inputting message input at a time is 1 and the number of outputs is 2, that is N is equal to 2. Okay. And since we have only one flip-flop, so it is 2 to the power of m states. So 2 to the power of 1 is, we have only 2 states, that is S0 and S1. So the binary description of S0 we have considered as 0 and S1 as 1. Okay. So and also, so this is the first step, that is you need to first write the state table. Then the second step is we need to write the state transition table. So state transition table consists of present state, its binary description, and what is the corresponding input to go to the next state, its binary description, and DL and DL minus 1, that means, so this is your DL and this is your DL minus 1. Okay, that means what are the inputs which are going to the adder. So it is DL and DL minus 1. Then we have two outputs, that is C of 1 and C of 2. So then we have constructed this state transition table by inputting the inputs to your flip-flop. That is, for S0 state, the binary description is 0. That means the flip-flop will be in the 0 condition, and if you input 0, the output will be 0, 0. So now if you change the input to 1, so what happens? The flip-flop change gets, it is going to go for the next state. So its state gets changed to S, that is 1. So 1 means it is S1 state, and the output also gets changed to 1, 0. It is DL and DL minus 1. Corresponding to that, so for the upper adder, so we are going to consider DL plus DL minus 1. So it is 1 plus 0, C of 1, it is 1. Similarly, so it is directly we are going to consider DL for C of 2. So whatever you are inputting, the same thing is getting across your output C of 2. So this is how we have constructed the state transition table. So now for the state diagram, so we have two states 0 and 1. So the present state is 0. So if the input is 0, what is its next state? It is S0. That means it remains in the same state with input 0. What is its output? It is 0, 0. So if you change the input to 1, so it goes to S1 state. So it is input 1, output is 1, 1. Next, from S1, if the input is 0, it goes to S0 state. So with output 1, 0. So with input 1, it remains in S1 state. With input 1, what is its output? It is 0, 1. Okay. So this is how we have constructed the state diagram. So now we need to write the code tree for the state diagram. So as we started with the previous case, the same thing. So S0 with two states 0 and 1. So it goes to S0. So if it is 1, it comes to S1 state. So now first you check whether the input, that is the message input, starts from 1 or 0. So it starts from 1 here again. So we can just extend this, the downward part of your code tree, that is S1, S0 with 1. So this again gets changed to 0, 1. So S1 with input 0, it is S0, this is S1. So input 0, S0, S1, so 0, 1, so it is S0, this is S1. Zero, 1, S0, S1, S0, S1. Okay. So now the first message input is 1. So for the input 1, you have to make a downward transition. So with S11, what is its corresponding output? S0 with input 1, the output is 1, 1. Okay, this is for the first message input 1. So now, what is the next input? It is 0. So that means it has to make upward transition. So this is for 0. What is its output? S1 with input 0, the output is 1, 0. What is the next message input? So the next message input is 1. So it makes a downward transition. So it is S0 with 1, the output is 1, 1. So this is for the third message input 1. So again we have 1. So that means it makes a transition to S1. Again the output is 1, 1. So now this is S1. With input 0 and 1. So S1, so it is S0 and S1. So this is 1 with output 1, 1. So this is for fourth input and this is for the fifth input. So it is 1, 0, 1, 1 and 1. So here we need to check whether the tail of the tree is, that means we need to extend the tail of the tree or not. So that means L into N into L plus M is N into L plus M. So N is 2 into length is 5 plus 1. So it is 6 into 2, that means 12 bits. So we have 10 bits which are represented, that means only one bit has to be appended. So here also we need to extend the tree further. So S1 with S0 and S1. So this is for input 0 and this is for input 1. So we are appending zeros further. So this is for appending 0. What is its output? So the output of this is, so S1 with input 0, the output is 1, 0. So what is the code we got? So C is equal to, so this one, so C is equal to 1, 1, 1, 0, 1, 1, 1, 1, 1, 1 and 1, 0. So this is the code what we have got. So now we need to verify so whether the codes what we have got is correct or not with respect to the time domain approach. Looking into the encoder block diagram, we have G of 1 and G of 2 is 1, 1 and 1, 0. So now looking into that, so we need to construct the generator matrix. So 1 and 1, 1 and 0. So rest we need to append it by zeros. So we have 12 bits now. So it is 0, 0, 1, 1, 1, 0, 0, 0. So 0, 0, 0, 0, 1, 1, 1, 0, 0, 0. Then we have 0, 0, 0, 1, 1 and 1, 0. So C is equal to D into G. So what is your D? So D is 1, 0, 1, 1 multiplied by G. So G is nothing but this one. So if you multiply that, you are going to get the same code. So if you don't get the same code, then that means that you have made something wrong with respect to the code tree. Okay. So this is how we are going to verify the code what you have found out from the code tree by using the time domain approach. Thank you.